All right, happy Thursday, Artesians. So our last lesson of the week. Today we're going to talk about how to predict the products of these simple reaction types. Predicting the products of reaction is a really valuable skill that we have as chemists. It kind of lets us be able to see into the future a little bit. We can think to ourselves, what would happen if I mix these two chemicals? And that's important to know because if we're going to make some sort of toxic gas, we want to know that before we mix the chemicals together. We can predict if we're going to make a precipitate or not. So just being able to know what's going to happen before it happens is a very important skill. So, taking a look at this slide here. The ones that we're going to do this the most often with are the replacement reactions, single replacement and double replacement. We can also predict a little bit the outcome of a combustion reaction. If I'm doing a combustion reaction and I have an organic fuel, and remember I said that organic means it's got carbon in it. If you burn an organic fuel, it will always result in carbon dioxide and water. You might make other things depending on what sort of fuel that you have. If you have fuel that has nitrogen in it, you'll probably end up making some sort of nitrogen gas. But for the most part, if you're doing a combustion reaction and you're burning an organic fuel, you're going to make carbon dioxide and water. So that's one really easy prediction that we can make. If we can identify it as combustion and we see that it has carbon in the reaction, we know we'll make carbon dioxide and water. As far as these last two, synthesis and decomposition, these are really the harder reactions to predict. You would have to know which chemicals are going to be stable and which chemicals will be unstable to know what would actually form. So I'm not going to test you on those. I'm not going to ask you to predict the outcome of a synthesis or a decomposition reaction. So there's three types of reactions that I want you to be able to predict. We just talked about combustion. If we're doing a combustion reaction and it's organic fuel, carbon dioxide, and water. The other two reactions that we're going to talk about, these are the ones we're going to focus on the most, are the replacement reactions. Single replacement and double replacement. I've got my quick example here for double replacement. So for example, if we had sodium chloride and potassium bromide, and we know that they're going to do a double replacement, we're going to replace the ions. We're going to switch those ions out. So instead of sodium chloride, we'll have sodium bromide. Instead of potassium bromide, we'll have potassium chloride. We can see that the anions switch places, or we could say the cations switch places. But they ended up bonded to the other ion that they weren't bonded with in the reactant side. So double replacement, those ones are nice and easy to predict too. If I'm telling you that it'll do a double replacement reaction, you're just going to go ahead and swap those ions. We'll see some examples of that too. Let's look at this next slide though. The activity series. This is a tool that we will use when we are predicting the products of a single replacement reaction. This is something that I'd like you to get on the back side of your periodic table, especially since we're doing this distance learning. I want you to have all of your tools in one place, and this activity series is one of those tools that we're going to use. This is not something that I have memorized. I know the general gist of it, but it's something that I need to reference too. So I don't expect you to memorize this. I expect you to have it written down so that you can reference it. But what does it even mean? Let's talk about what we're actually looking at here. We can't use it if we don't know what it is. So the activity series. This is listing mostly metallic elements in series of their reactivity. How reactive are they? Remember that when I'm talking about reactivity, I'm talking about the willingness to react. How likely is it to react? If something is reactive, it means it's unstable. If something is non-reactive, that means it's stable. Stable things are less likely to react. Unstable things are more likely to react. So if we're looking at this, we can see that it places potassium at the top. Potassium is a very reactive metal. We saw that. We did a little potassium explosion at the beginning of the year. Right underneath that, it's got sodium. Sodium is also a very reactive metal. And then we keep going. Calcium, magnesium, aluminum, zinc, iron, tin, lead, hydrogen towards the bottom here. And then copper, mercury, silver, gold, and I think platinum would be right underneath that. So we can see that some metals, like silver or gold, are really not that reactive, which means that they're actually pretty stable. But then some metals, like potassium, sodium, calcium, magnesium, are very reactive, and we're going to see them react a lot. So let's read this last sentence that I wrote here. If the element is less reactive than the metal in the compound, then there will be no reaction. We're talking about single replacement reactions here. And I'm going to say this a few times, give you a chance to get it in your notes, give you a chance to really understand it. Remember, in a single replacement reaction, we've got an element in its elemental form, and that's going to react with a compound. A compound, something contains more than one element. So if we've got our elemental form, that's just an element by itself, it wants to react with a compound. This activity series is going to tell us if it'll actually react or not. Some single replacement reactions actually just don't react. If you take a stable metal and try to react it with maybe a compound with potassium or sodium, that stable metal is just going to stay by itself. It's already pretty stable. And then the potassium or the sodium, the more reactive metal, it's being stabilized by being in that compound. Being in the compound is the more stable form, so it's not going to switch over to its elemental form. It's going to stay where it's stable. And then the gold or the silver will also stay where it is stable. Now let's talk about the reverse. What if I had a very reactive metal, like we'll say calcium? I've got a very reactive metal, calcium, and I'm trying to react it with a silver compound. It's a compound that has silver in it. Silver's not very reactive. So if I'm thinking about a reactive metal in its elemental form, like calcium, reacting with a silver compound, a relatively stable compound, that more reactive metal, calcium, is going to switch in. It's going to replace the silver because being in the compound will help stabilize the calcium. And the silver is already pretty stable on its own. It doesn't necessarily need to be in a compound to have that stabilizing effect. So definitely pause the video if you have to. Copy down this reactivity series on the back side of your periodic table. And then I'm going to switch here. And I'm going to start doing the rest of this lecture on the whiteboard so that you can see sort of this reactivity series in action. And you can see how can I use this series to tell if a reaction happens or not? How can I predict the future to know what sort of reactions I'm going to see take place? So that's what we got up next. Let's see if we can't predict the future. Let's see if we can't predict these products. All right, so we're going to start it off with one of the easier ones to predict. What I'm looking at here is a combustion reaction. How do I know this is a combustion reaction? It's reacting with oxygen gas, O2. If we're reacting with that oxygen gas, that's a pretty clear sign that it's going to be a combustion. It's also an organic combustion. I've got some carbon that I'm using as part of my fuel. So this is an organic combustion. This is the combustion of methane. So how can I tell the future? How can I know what my products are going to be? This is one of those ones that we talked about. In an organic combustion, your products are always going to be carbon dioxide and water. Carbon dioxide and water for an organic combustion every time. Now, this reaction is not balanced yet. Remember that yesterday we talked about how to balance these reactions. Over here I've got 4 hydrogens. Over here I only have 2 hydrogens. So it's not balanced yet. I would need to give coefficients to really truly finish out this reaction and make it sound. So I'm going to switch colors here. And let's see if I can't figure out what coefficients can I use to balance this reaction. Always start with carbon. 1 carbon over here. 1 carbon over here. Carbon's good. Now we'll go to hydrogen. 4 hydrogens. Only 2 hydrogens over here. I need it to be the same to obey the law of conservation of mass. So I'm going to double it up over here. If I'm producing 2 molecules of water in every iteration of this reaction, that's going to balance out. 4 hydrogens. 4 hydrogens. Finally, I'll look at the oxygen. On my product side, I've got 1, 2, 3, 4 oxygens. 2 from the carbon dioxide, 2 from the water, because I've got 2 molecules of water, for a total of 4. Right now I've only got 2 on the reactant side. To make it even, I'm going to put a coefficient of 2 here as well. Now I've got 4 oxygens, 4 oxygens. 1 carbon, 1 carbon. 4 hydrogens, 4 hydrogens. I've predicted this reaction and I've balanced it. This is a really useful skill. So I could say, I wonder what will happen if I mix this methane with this oxygen. Well, I know what'll happen. I'm gonna make carbon dioxide, and I'm also gonna make quite a bit of water. So that's the easier one, the organic combustions. Let's try some of those replacement reactions and see if we can't predict those as well. Alright, so taking a look at another one here. So I would go ahead and tell you that this is a double replacement reaction. And then I would ask you to tell me what's going to be the products of this double replacement reaction. So I know it's a replacement reaction. So I know that something's going to end up switching places here. They're going to replace each other. Looking at my 2 reactants, I've got calcium chloride and sodium carbonate. Remember that this is a polyatomic ion, carbonate. I'm going to treat it like 1 ion because it is 1 ion. So now my job is, I need to decide what are the products going to be. I need to predict the future a little bit. You need to switch the ions. So, one way that I've seen people do this is they say to do the inside and then the outside. So I'm going to take this chlorine and I'm going to bond it to that sodium there. And then I'm also going to take this calcium and I'm going to bond it with the carbonate. So I like this inside-outside method, and it is effective pretty much all the time. Just waiting for that really loud truck to go by. Okay. So I know that one of my products is going to be this compound between sodium and chlorine. And then my other product is going to be the compound between calcium and carbonate. I'm switching them. I'm replacing them. So if I do my one in blue here first, I can't forget what I've already learned. I still need to use these common oxidation states, these common charges. For sodium, it's going to be a +1. That's on the front side of your periodic table. For chlorine, it's going to be a -1, also on the front side of the periodic table. A +1 and a -1, these already cancel out. So my compound is just NaCl, sodium chloride. And then if I'm looking for the compound in red here, between calcium and carbonate, calcium will have a +2 charge from the front side of the periodic table. Carbonate will have a -2 charge. That's on the back side. That's on the polyatomic ion list. +2 and -2, these already cancel out. So my compound is calcium carbonate, CaCO3. Now again, this is not balanced yet. 2 sodiums over here, only 1 sodium here. 2 chlorines here, only 1 chlorine here. I'm just going to need to put a coefficient in here to make sure that it's a balanced reaction. Now it's good. 2 sodiums, 2 sodiums, 2 chlorines, 2 chlorines, 1 calcium, 1 calcium, 1 carbonate, 1 carbonate. So I've done it. I've predicted the products of this reaction. I'm going to make 2 molecules of sodium chloride and 1 molecule of calcium carbonate. Let's take a look at we'll do 2, I think, examples of single replacement reactions. Because those might be the harder ones, the single replacement ones. We're going to do 2 more. Okay, so predicting the products of a single replacement reaction. First of all, how do I know that this is a single replacement reaction? Well, the calcium over here is in its elemental form. It's by itself. In the last example, I had 2 compounds that were going to react together. This time I've got 1 compound and an element in its elemental form. It's solo. It's single replacement. This is when I need to use the activity series. That's why we copied it on the back side of your table. This is actually the same example that I used earlier in the video. I've got 2 metals, calcium and silver. If I check that activity series, calcium is more reactive than silver. So this reaction is going to take place. Calcium's more reactive. It's going to cause these 2 chemicals to react. So, my 2 metals are going to be the ones replacing each other. The calcium and the silver will end up switching out, replacing each other. So let's think first about what my elemental form will be. Calcium was by itself. Now silver is by itself. Silver's in its elemental form. This is good. Silver is more stable in its elemental form than calcium is. It's that stability that's driving this reaction to take place. Now let's think about the compound that we made. Calcium was by itself, so now it's going to be part of our compound. I know I'm going to see this mistake be made. People are going to show me something like this. CABR. We can't forget what we've already learned. This is not a balanced compound. This is not what calcium bromide looks like. Calcium has a common oxidation state of +2. Bromine, common oxidation state of -1. These don't cancel each other out. I need to have 2 bromines in order to make this reaction balanced, or in order to make this compound on its own balanced. So calcium bromide is CaBr2. I need 2 bromine atoms to cancel out the charge from the calcium. So I've predicted my products. I know I'm going to get elemental silver and calcium bromide. But this reaction's not balanced quite yet. 1 bromine, 2 bromines. Better double it up over here. Now I've got 2 bromines and 2 bromines. But now I've got 2 silvers and only 1 silver. So I've got to double up the silver as well. This is my balanced and predicted reaction. 1 calcium, 1 calcium. 2 silvers, 2 silvers, 2 bromines, 2 bromines. Not only have I predicted what will happen, I've also been able to predict what ratios it'll happen in. I'll make 2 atoms of silver, or I'll produce 2 atoms of silver for every 1 molecule of calcium bromide that I'm producing. Let's look at one more example, and then I think we'll be good. Alright, my last reaction here. So, this is another single replacement reaction. How do I know it's single replacement? Magnesium is in its elemental form, and it's set up to react with a compound. Since we're doing single replacement, we need to think about that activity series. I've got 2 metals here, magnesium and potassium. I check the series. I check to see which one is more reactive. This time, the potassium is more reactive than the magnesium. Potassium is extremely reactive, very unstable on its own. So, the more reactive metal is already in the compound. The more stable metal is already in its elemental form. This reaction actually will not happen. There's going to be no reaction if I were to mix these 2 chemicals. If I had a solution of potassium sulfate and I dropped some solid magnesium metal in there, it would sink to the bottom and it would do nothing. It would not react. And that's because it's already more stable in this configuration than if I replaced them. If I actually did that replacement, it would end up becoming more unstable. The universe is trying to stabilize. It wants the more stable chemicals to be the ones that are present. So it's not gonna drive itself to do this unstable reaction. I can put NR for no reaction. If you want to write the whole thing out too, whatever, that's fine. No reaction. Or no RXN. RXN for reaction. However you want to show me. Most of you are just going to put NR, but it's showing that nothing happened here. I can go ahead and try to mix the magnesium and the potassium sulfate. No reaction. Nothing's going to happen. So we definitely want to use that reactivity series anytime we're trying to predict a single replacement reaction. We've covered a lot this week. Trying to cover the same amount of material that I would do in 5 days in person, and I'm trying to do it in 3 days from a distance. It's a little bit of a challenge. You don't have a homework for tonight, but I have released the reactions quiz, which is a Google form. You can get to it through Google Classroom. That reaction quiz, it is 5 questions. They're all multiple choice. I'm trying to make it a little bit nicer, a little bit easier, given the circumstances. So make sure that you get that quiz done by midnight on Friday, which will be tomorrow for you. You only get one chance at that quiz. It is a locked quiz, so it won't let you do it again, and it won't let you get onto other tabs. But I'm still doing quiz retakes. So if you take that quiz, you're not happy with your grade, email me or talk to me during office hours. I'll send you the second version of the quiz, and then you get one shot at that as well. So I'm still giving you quiz retakes. I'm even making the quizzes easier given the circumstances. But make sure that you're giving that quiz a good attempt, and that you're getting that turned in on time. Your oxidation state lab report is also due Friday at midnight. Email me if you have questions. Come to office hours if you have questions. And I can definitely help you out with that. Also, don't forget that you can use that chemistry chat room. Maybe you're struggling with it, but maybe somebody else really gets it, and they would be more than happy to help you out. I know that some of you have already been sharing your lecture notes on that chat room. Shout out to Lily Bright and Savannah Prater. Really appreciate that. Definitely share your lecture notes. Share your resources. We're in this together, so we should act like it. We should not be acting like we're alone in the dark, because that's not reality. All right. That's it for this week. I will see you again next week, or maybe I'll see you in office hours. I hope I do. Stay safe, stay classy, Artesians.